Yes, that's the tension, isn't it? Is that we don't want to be avoiding one hazard like turbulence, and by doing so, creating a contrail or something. That's not ideal. And we don't want to be avoiding a contrail, but flying into a turbulent region. I think what we need to picture is something like a cost function that has in it turbulence and contrails and storms and lightning and volcanic ash and all the hazards and all the things we don't want to an aircraft to be creating, and write them down in a sort of equation.
Welcome to the Aerospace Ambition podcast. In this episode, we'll explore the impacts of climate change on aviation. I'm Marius, an aerospace engineer and your host. Well, first off, I have a special surprise for the audience today. Kieran, who all of you know, will be joining us today. So welcome, Kieran.
Thank you, Marius. Thrilled to be back.
Glad to have you back, and I'm pretty sure you will like our guest today, because we have the pleasure of hosting Professor Paul Williams. Paul is Professor of Atmospheric Science at the University of Reading. Educated in physics to PhD level at Oxford, he specializes in atmospheric turbulence, jet streams, numerical modeling, and climate change. He co-developed an award-winning aviation turbulence forecasting algorithm that is now being used operationally, and he has pioneered research into the effects of climate change on turbulence. Paul, welcome to the show.
Thank you very much, Marius and Kieran. It's so great to be on the podcast with you both. I've listened to many of your previous episodes, and I'm thrilled that it's my turn today to say a few words.
Thank you.
Very kind of you, Paul. Great to have you on the show. So first off, we have a question for you is, do you fly? And if yes, do you ever take your seatbelt off during cruise?
I do fly. I fly a lot. I fly around the world to speak at science conferences, and I also collaborate with scientists internationally. Science is, as you both know, an international business, and it involves a lot of travel. And of course, that's a bit problematic and ironic in the context of our subject today, isn't it? Because we're trying to, many of us, fly as little as possible, or to at least reduce the environmental impacts of flying. But no, I fly a lot, and you should see how quickly I fasten my seatbelt when I get back from a toilet break. If that was an Olympic sport, I would have a gold medal, because I am fully aware of the crucial role that seatbelts play in passenger safety. So yes, I always keep my seatbelt fastened. If I go for a quick stretch of my legs, the millisecond I get back to my seat, I'm buckled up again.
Straight back on.
Wow. I was expecting a certain kind of an answer, but I wasn't expecting, this strong metaphor here. And this nicely leads on to the first question, which is the obvious question here. But I remember in May, I was on vacation with a friend who is an airline pilot. And we were having lunch when he told me about the news about a flight that has experienced severe turbulence. And also at the same table was another friend, and she's afraid of flying. So when she heard about that news, the turbulence on that flight, she immediately was afraid, which I kind of understand, given her fear of flying in general. But then when I spoke to my friend, the airline pilot, and he told me that, this was a severe thing, that really made me thinking, and that really made me concerned. And then I started looking into it. So for our audience, since you've probably investigated this into very technical details, what was this flight of Singapore Airlines about? What happened, and what are the odds of something like that happening again?
Great questions. And we don't have all the answers yet. I'm sure there will be many academic studies on that particular turbulence encounter in the coming months and years. What's clear is that the turbulence would be categorized as either severe or extreme. So we do have this kind of calibrated strength scale for measuring how strong the turbulence is. A bit like, the Richter scale for measuring how much energy is in an earthquake, for example. It doesn't have a name for turbulence. I don't think any scientist wants this scale named after them because it's such a horrible sort of scale, isn't it? But we do have a scale, and it goes from light to moderate to severe to extreme. And the definition of severe is that the upward and downward motion of the aircraft will have an acceleration that exceeds 1 g. So stronger than gravity. And so in severe turbulence, if you're not seat belted, the aircraft will be moving down more quickly than gravity can keep you in your seat. In other words, you'll become a projectile. So it's severe that has the potential to cause injuries, and extreme, the next one up, really, quite serious injuries, whereas the light and the moderate, nervous flyers don't like them, but they're not going to cause any injuries. So what we know about the Singapore encounter was that it must have been at least severe, judging from the injuries, if not extreme. We don't yet know exactly in detail what kind of turbulence it was. There are different kinds. There's obviously flying through a storm is obviously turbulent. Flying over a mountain range can also be quite bumpy. And there's another kind called clear air turbulence that can happen away from storms and away from mountains, where you have strong air currents called jet streams, and they can become unstable. I don't think we know yet which category of turbulence caused that particular encounter. Usually the most of the clear air turbulence is in the mid latitudes, because that's where the jet streams are. Which is not to say that you can't have clear air turbulence closer to the equator. But I think we need to do a bit more digging before we have all the answers. I do know, though, that it must have felt awful. It must have been terrifying for those on board. I've had a look at the data, and at one point, there was a period of 4.6 seconds in which the aircraft fell 178 feet in 4.6 seconds. So that's an average speed over that 4.5 seconds of 26 miles an hour downward. It must have been like being inside a washing machine and just being thrown around for anyone who wasn't seatbelted. And I'm not surprised that we had those dozens of injuries and sadly a fatality as well.
I think that's certainly enough to put even the bravest flyers off some flights. And I'd say the Williams scale certainly has a nice ring to it.
No, I don't want it named after me.
Okay. Yeah, understandable. So I think what we're going to do now is just take a step back and look into what effects there actually are in terms of climate impacts on aviation. So could you just give us a little rundown of the different kinds of effects and phenomena that occur on a high level, and maybe which effects you're most concerned about?
Absolutely. And that one question could fill up the entire podcast, in fact, although I'll try and keep it brief. But it's such a big question that we could talk for an hour about it. And indeed, I do give 1 hour long seminars on it. And it's interesting because I know many of your previous podcasts in this series have focused on contrails and on aviation impacts on climate. So I guess this is an opportunity to turn that on its head and look at it from the other side. In other words, if we don't manage to reach net zero or reduce the radiator forcing from aviation, what will be the consequences? The consequences for climate, but then those feedback consequences on the aviation sector itself. So I think there is actually a selfish reason for aviation to decarbonize, because it will be a victim of climate change as well as causing it. Of the many possible impacts, I think 5 possible impacts of climate change on aviation have been studied. And so we have some numbers. So one of those would be at ground level at the airport, rising sea levels threatening to flood the airports. So that this can happen. Many airports are just a few feet above sea level, especially coastal airports. And there are many airports that are coastal because that's where many of the large population centers are. So we know that, for example, over 30 European airports are going to have their runway capacity threatened by sea level rise, according to Eurocontrol. And you might remember a few years ago, Hurricane Sandy, this was back in 2012, came up the east coast of North America and flooded New York City and closed down LaGuardia Airport for a few days because both the runways were underwater. So a combination there of sea level rise plus storm surges and heavier precipitation could be problematic in future, and indeed it already is problematic, could be even more problematic in future for aviation. A second impact at the airport is takeoff conditions become a bit more challenging as the air warms up, because as air gets warmer, it gets less dense, and so there's less air for the wings to cut through as they're trying to take off, and so they can generate less lift. Actually, it's 1% less lift for every 3 degrees of warming. And so we know that there have already been examples where it's been so hot that the plane has been too heavy to take off and passengers have had to be bumped off their flight. It's quite rare, but I think it's something we'll see more frequently in future. We've recently calculated that the maximum takeoff weight of an Airbus A320 at an airport in Greece has been reducing by 132 kilograms every year for the past few decades. And so over the 30 years since that aircraft model came into service, that equates to a 4,000 kilogram or a 4-ton reduction in the maximum takeoff weight. So I think we'll see that effect continuing into the future as well. We might see moving up now. So suppose the airport's not flooded. Suppose the plane can take off and you get airborne. A third impact could be more severe weather, more lightning strikes. We know that there's a relationship between heat and lightning. There's more lightning in hotter countries than colder countries, etc. More in summer than winter, more in the middle of the day than the middle of the night. So clearly heat is driving lightning in some sense. And there is a prediction of 12% more lightning for every 1 degree Celsius of global warming in the US. So that's not great news. And there indeed has already been an observed increase in lightning, for example, in the Arctic Circle, where lightning is very rare. Historically, it's usually too cold, but lightning has increased massively in the Arctic Circle over the past decade or so. And then impact number 4 is impacts on the jet stream, which is important for turbulence, and I'll come back to that. That's going to be my impact number 5. But impact number 4, it's the headwinds and the tailwinds, these powerful air currents blowing at 150, 200 miles an hour. This is, of course, the reason why eastbound journeys are usually a lot faster than westbound journeys. Well, the jet stream is changing because of climate change. And we project that its speed is going to increase on average. And so that will mean faster eastbound journeys, slower westbound journeys because of the stronger headwinds. And then finally, moving on to the thing I've studied personally the most, which is the turbulence. And it turns out that, well, clear air turbulence specifically is generated by wind shear. And what's wind shear? Well, it's increases in wind speed with altitude, and we get that a lot in the jet stream. And it turns out that climate change is increasing the wind shear in the jet stream. We know that today there's 15% more wind shear than there was in 1979 when satellites first began observing the North Atlantic jet stream. And we also know that today there's 55% more severe clear air turbulence over the North Atlantic, 41% more over the USA, and similar figures around the world. And the projection for the future is that the amount of severe clear air turbulence could double or treble in some parts of the atmosphere in the coming decades as the wind shear continues to increase. So lots of bad news there. Maybe in principle, there could be some benefits of climate change to aviation. I haven't come across any yet. All of the impacts that have been studied seem to be on the negative side. And I think we're looking at a future with more lightning, with more turbulence. And that's assuming the aircraft can get off the ground because the air's not too hot, and assuming the airport wasn't flooded. So many possible low probability, but high impact events there in projected in the future for the way that we fly.
Well, perhaps a sub 5-hour flight time from JFK to London Heathrow is one benefit out of the many negatives.
Yes, that's true. And in fact, we have already had that. That record keeps being broken. The eastbound subsonic transatlantic crossing time from New York to London used to be 5 hours and 16 minutes. And then it was 5 hours and 13, which was just a few minutes shaved off. But the next time it was broken, it was well and truly smashed. In fact, it's now 4 hours and 56 minutes as of a couple of years ago. And I think we might see that record being broken again and again as the jet stream continues to accelerate.
Yeah, so in preparation for this interview, I actually watched one of your presentations back, and it must have been from like 2018. And you were saying you didn't think that we would ever see that in our lifetimes, and we've broken it within a few years.
Absolutely. And in fact, a journalist once asked me, will we ever see a sub 5 hour eastbound flight? And I ummed and eventually I sort of said no, or I refused to answer. I dodged the question. I wish I'd said yes, because indeed it has come true now, and we have had that sub 5 hour flight.
I recently was on the car with my father and talking about, climate change and aviation as you do. And I told him about this phenomenon. He flies quite a lot. And so I told him about this phenomenon of turbulence and the phenomenon increasing now with the climate changing. And he asked me, yeah, but why do you have turbulence? And I really tried to explain it and break it down in very simple terms. I started talking about like buckets of air and really try to make it very tangible. Probably you could do that much better than I did. How would you explain it to a non-technical person what the turbulence is and how does it come about?
Yes, it's a good question. And well, it's an easy question to ask. It's a difficult question to answer because turbulence has been a problem in physics for decades, or in fact centuries. In fact, it's been called the hardest problem in classical physics. The equations are nonlinear and virtually impossible to solve on paper, which is why we have to use computer models. It's really a thorny, grand challenge scale of problem in physics. But essentially, all turbulence is random swirling motions in fluids. So all liquids and all gases have the potential to become turbulent. But you're more likely to see turbulence in some fluids than others. You're more likely to see it in a swimming pool or a cup of coffee than you are in a jar of honey. And that's because if the fluid is too thick, like honey, all the energy that might otherwise go into creating turbulent currents gets dissipated away by the viscosity. So, of course, there's turbulence in the atmosphere all the time, everywhere, really, but usually it's too weak to be noticeable until it gets locally generated or increased by storms or strong air currents becoming unstable. And these air currents collide with the airframe and they push it around, mostly in the up-down direction. Because if you think about looking at a plane from behind or in front, you can't see very much cross-sectional area. If you look at it from the side, you still can't see very much cross-sectional area. It's when you look at an aircraft from below or above, because of the wings and their great area, that's when you see the most area. And so that's where that's the direction in which the turbulence can do the most damage and create the most acceleration and movement. So we have these currents in the air. They push up and down against the wings of the aircraft, and that's what causes a bumpy flight.
To what extent is this a predictable phenomenon versus a maybe more stochastic or chaotic situation? Is there how much can we actually predict and forecast these turbulent events?
It's a great question, and we do predict it. We do forecast it every day. Before takeoff, pilots will consult what's called a significant weather chart, which will have various hazards. Could be volcanic ash, could be storms, could be clear air turbulence. And the forecasts are pretty good. I mean, like all weather forecasts, they're not perfect. They're not 100% accurate all the time. When I started out, when I did my PhD 20 years ago, we could successfully forecast about 50 to 60% of all clear air turbulence. And in fact, I talked to pilots 20 years ago who told me they just ignored the forecasts because they were so unreliable. Today, because of 20 years of research into what generates turbulence and how to forecast it, today we can correctly forecast more like 70 to 75% of all clear air turbulence. Still not perfect. It means that for every 4 patches of turbulence out there, we can correctly forecast 3 of them, but that leaves 1 that even the best forecasting tools today cannot forecast. So we've got more work to do, but I would say the forecasts are very useful now. And I've never met a pilot recently who says they completely ignore them, which I did 20 years ago.
Yeah, so I guess it's the aviation industry's job to try and outdo these increases in turbulence through better forecasting and prediction.
Yes, and quite what happens remains to be seen. All I'm saying is there's more turbulence in the atmosphere, and there will be more turbulence in the atmosphere. That doesn't necessarily mean there'll be more turbulence on flights, as you say, Kieran. If we can get better at forecasting and avoiding the turbulence, and pilots are experts at doing this, of course, then we could have twice as much turbulence in the atmosphere, but no increase in turbulence on flights. Whether that happens remains to be seen. It's a big challenge, and it will take a lot of work.
So we're just now going to cover the question from Dr. Vincent Meyer from last week's episode. And he asked, what is the relationship between clear air turbulence regions and ice supersaturated regions where persistent contrails form? Is there the risk to avoid one thing and divert into another, or do we see some synergies occur here?
That's a fascinating question, and I think that question is worth an entire PhD project and someone studying it for 3 years, because I certainly don't know the answer, and I don't think anyone knows the answer. It's something I've discussed before with colleagues. So I don't know. We'll have to wait and see, I think, to some extent. Of course, yes, that's the tension, isn't it? Is that we don't want to be avoiding one hazard like turbulence, and by doing so, creating a contrail or something. That's not ideal. And we don't want to be avoiding a contrail, but flying into a turbulent region. I think what we need to picture is something like a cost function that has in it turbulence and contrails and storms and lightning and volcanic ash and all the hazards and all the things we don't want to an aircraft to be creating, and write them down in a sort of equation, and find the flight route that minimizes the cost of the route as measured by that cost function. There are difficult choices there. It means you have to decide, you have to pit turbulence against contrails and say, how bad is this compared to that? How much is it worth a little bit of light turbulence to avoid a short-lived contrail? These are difficult questions. There's no simple answer. I don't think there's an objective answer. I think it's all subjective choices that someone was going to have to make. And the other thing in the cost function would just be the fuel burn of the flight. We, of course, want to minimize the total amount of fuel, which usually means the shortest route through the fastest tailwind. But if there's turbulence there, or if that involves creating a contrail, to what extent is it worth deviating and adding 10 minutes onto the flight to avoid some turbulence or a contrail? I don't know. These are tricky questions, and I don't have any easy answers right now, I'm afraid.
Yeah, these are very tricky questions, and I hope for the next question we don't need another PhD as for the previous question. I mean, eventually it comes down to, do you like flying? That's one thing. And can you afford flying? Those are the two main drivers, I would say, to make the decision of flying. And so zooming out completely here, what do you think are the long-term implications of increasing clear air turbulence for, well, passenger comfort, but also for airline economics?
Interesting question. I think that is worth another PhD project, but I think it needs some thought. I think many of us like flying and don't want to give it up, but of course we want it to be sustainable. Aviation brings immense benefits to the world in terms of connecting communities and promoting economic development. And I don't want to see a future where nobody flies, although there are some who clearly do want to see that future. I want to see a future where flying is available to everyone, but is sustainable and is net zero. And we need to work as hard as we can, as quickly as we can, to achieve that. In terms of the economics to the airlines, I mean, there is some technology out there that could help us, especially with turbulence. The storm-related turbulence does show up on the flight deck, on the radar, on the weather radar, but the clear air turbulence does not. So it's literally invisible. You can't see it through the window, can't see it on the radar. But there is a technology called LIDAR, which, if you use the right wavelength of light, can get reflected by density anomalies ahead of the aircraft, 20, 30 miles ahead of the aircraft, and show up as an echo on a screen. And so they've done some test flights, and this technology can make the invisible clear air turbulence visible in the flight deck on a screen 20 to 30 miles ahead, which is just enough time to put the seatbelt sign on and secure the cabin. This could be a really, really a game changer and could help us avoid a doubling in the turbulence in the atmosphere, translating into a doubling in turbulence on flights. But it's expensive and it's a big, heavy box. There isn't enough room for it in the nose cone. So the technology needs to get miniaturized. The cost needs to come down. And then we might see airlines opting to retrofit their existing fleet of aircraft with LIDAR. That could revolutionize the way we fly. And there'd be no excuse for any aircraft ever encountering clear air turbulence if it had this technology installed on it. It could be really revolutionary. But at the moment, the business case is negative. It would cost an airline more to fit it than they would save through the avoided turbulence.
So how much have these algorithms that you co-developed helped to reduce severe CAT events since their implementation? Do you have any statistics that you can provide on that?
Yeah, so I've been involved since my PhD in co-developing some turbulence forecasting algorithms using improved knowledge on what is actually generating clear air turbulence. Turns out it's not just about wind shear. You can have a kind of wave called a gravity wave that can propagate through the atmosphere, and even if the amount of shear in the atmosphere is not strong enough to generate turbulence, the presence of the gravity wave can increase the shear and tip the system over into becoming turbulent. And so by using knowledge like that goes back to my PhD 20 years ago, we have developed a new algorithm that shows a lot of skill, and it's currently being used. In fact, it's been used every day since October 2015 to produce significant weather charts for pilots and result hopefully in smoother journeys. So we've estimated that there are 120 million fewer passenger hours spent in turbulence to date. So that's 120 million passenger hours that would have been spent in turbulence if we hadn't had this discovery, that have been prevented from flying through the turbulence because of that forecasting algorithm, and 1 million tons of carbon dioxide emissions saved as well, because every time a flight encounters turbulence, it makes a deviation, and that adds to the fuel burn and the flight time. So, but there's lots going on. So there's better turbulence algorithms trying to reduce the amount of time aircraft spend in turbulence, but then there's climate change increasing the amount of turbulence in the atmosphere. There's changes in aircraft design. Modern aircraft are better at responding to turbulence than the previous generation of aircraft, which used to bounce up and down a lot more because they had more rigid wings. So lots of things are changing on these decadal timescales, and it's quite hard to tease out cause and effect. So as to what happens in future, I think we'll just have to wait and see.
So just to recap on that, you were saying 120 million hours of flight time have avoided turbulence since the implementation.
Yes.
So what sort of timescale has that been over?
That's been since 2015. So it's coming up to a decade now. And it was in 2015 that the algorithm became operational and we started counting. It's just an estimate. It's very hard to get robust figures, but that's the best estimate we've been able to come up with. 120 million.
No small amount.
Yes.
Okay, so that brings me on to a next point is, do you think we'll ever reach a point? So, of course, westbound flights going from America to the UK and to Europe, they tend to take a lot less time due to the fact that the jet stream tends to move in that direction. However, when you go westbound from Europe to America, quite often you face extreme winds going in the other direction, meaning that it takes a lot longer to fly in those directions. So do you think we'll ever reach a point where westbound flights, or at least some westbound flights, can no longer take off due to not being able to reach their destination safely due to a lack of fuel carried on the aircraft? Yes,
that's a good point. And that certainly is an effect in terms of longer westbound journeys. One simple solution is just put a bit more fuel in the aircraft. That's not always possible. So we'll see. I think there have been, I'm aware of a period a few years ago, I think it was January 2015, when, well, partly it was when eastbound flights broke that record and shaved a few minutes off the fastest eastbound trip. But in the same 3 or 4 day period, some westbound flights from Heathrow to New York took off with what should have been enough fuel, but the headwinds were so strong that the flight was taking a very long time, and they had to actually make an unscheduled refueling stop in Maine. They realized they weren't safely able to reach New York because they burnt so much fuel. I'm not quite sure what happened then. We can forecast the jet stream, and we should have known 12, 18 hours ahead of time that the jet stream was going to be very strong. Maybe it was a poor forecast, not quite sure. But I have heard anecdotally of other stories where people flying from the East Coast to the West Coast of the US have had to make an unscheduled refueling stop because the jet stream's been blowing too strong. So I think that's the kind of thing we'll see more of in future. And if it's not possible just to put some more fuel on board, then there'll have to be an unscheduled refueling stop. It will mainly affect long haul routes, of course, where we need lots of fuel just to reach the destination, even if the jet stream wasn't blowing very strongly.
So maybe a contingency in the future would, rather than to cancel the flight altogether, would be to say, okay, we got to make a scheduled stop at this airport along the way and sort of do a short hop or 2 short hops to make it to your destination if the plane simply couldn't carry enough fuel.
Yes, something like that. I must stress, I think this is not going to happen every day. It's going to be on those rare days when the jet stream is blowing really fast, and catches us all by surprise. So it's not going to be something that we all experience on every flight we take. It will be marginal cases where the jet stream is blowing strongly and the flight route aligns perfectly with the jet stream. So that happens quite rarely. So it's not going to be an everyday occurrence. But yeah, I can see it happening more often.
Paul, as you can tell, we're trying to put in your research findings, which give us, relative changes, or relative improvements of models, for example, into absolute terms, because Kieran just asked the absolute question, can the westbound flights still work? And I have another absolute question to wrap up this episode, and that is with regards to tipping points. But tipping points not as you usually use the term for, the climate change and the global temperature, but more like the public perception. And you're not only involved in research, you also have experience in, answering questions from the media. This one flight that we discussed in the beginning, created a lot of attention in the media. And do you think, or do you expect that there could be a tipping point, an event, or even a series of events that could make people think about flying differently in a more dramatical or more radical fashion?
Interesting. I think in a changing climate, it often takes a disaster or a major extreme event in order to get people's attention. We see that with, for example, heat waves. For a lot of time, there was a lot of denial about. There's a skeptical community out there who deny that heat waves are getting worse because of climate change. But then we very clearly see that they are, and we see people dying because of the heat. And it takes events like that to focus the mind, sadly. And I do think that the recent 2 or 3 serious turbulence encounters just a few weeks apart, which is quite unusual, and including a fatality, which is very rare, has certainly got people talking. It's got people talking about what to do. Do we need to enforce compulsory seatbelt wearing on flights? That's something that's being talked about. It's a bit crazy, isn't it? If you're driving your car down the road at 20 miles an hour, you must wear a seatbelt. There's nobody who'd be driving their car and say, oh, you know what, I'm just going to take my seatbelt off driving down this motorway because I want to be a bit more comfortable. We wouldn't in a million years do that, and the law doesn't allow you to do it. But on an aircraft at 40,000 feet at hundreds of miles an hour, it's okay to take your seatbelt off as long as the seatbelt sign is not on. Is that acceptable? I don't have the answers. It's well above my pay grade, but it's the sort of thing that people are starting to talk about, including some senior leaders at some of the airlines. So who knows what the future holds? Nobody should not fly because of turbulence. I would always stress that. There are lots of nervous flyers out there. Severe turbulence is very rare. Less than 0.1% of the atmosphere has severe turbulence in it. So your flight is almost certainly not going to encounter it. So I would discourage anyone from not flying because they're worried about some of these effects. That they're all small probability, but admittedly high impact events when they occur. So people should still fly if they want to fly. But as I've said, the industry really needs to decarbonize rapidly. There are people now, there's a flight shaming movement. There are people who refuse to fly. I have friends and colleagues who haven't flown for years, if not decades, and take the train everywhere if they want to travel across a continent. So I think the aviation sector is part of the problem, but also part of the solution here. It's a small contributor to climate change, and it really is small currently, just 2%, 3% or whatever, however you measure it. But the rest of the economy is decarbonizing very nicely, thank you. But aviation is struggling, and it's going to struggle. But it's a massive challenge that we need to tackle. And some of the smartest brains in the industry are working hard on decarbonizing aviation so that we can continue to fly in future and enjoy all of the benefits without having the guilty conscience of generating more climate change. So it's an interesting future ahead, and I can't wait to see what happens.
What a great and inspiring summary, and also call to action here. Thanks for that, Paul. And in the tradition of the podcast, you've already been asked a question from the previous guest, and you can now ask a question to the next guest. And the next guest will be someone from the Rocky Mountain Institute, and that is Andrew Chen.
Well, I have a question for Andrew, and it's kind of a big question, but those are my favorites, maybe unanswerable. But it's a question really about policy and accounting for non-CO2 forcing from aircraft, because of course we have 𝐥𝐤𝐤𝐞 from ICAO, the international agreement on reducing carbon dioxide, and all of the focus has been on carbon dioxide. But of course we know that the non-CO2 part of the problem is a large fraction. And I just wonder, and contrails are outside my main expertise, but have we reached the stage yet where we understand the science well enough and they're able to forecast contrails and where they will be and where they will not be and what their radiative forcing will be? Have we reached a stage where we can imagine a version 2 of 𝐥𝐤𝐤𝐞, which includes the non-CO2 effects, the contrails, etc., and doesn't just focus on the carbon dioxide? That's my question to Andrew, and I'm very interested to hear his answer.
That's certainly a good one, and I will definitely take it on. Another quick question would be, because Andrew is already set in stone, he will join the podcast, but is there anyone else that you think, would be suitable in the line of this podcast as a guest?
Aha. Well, I know you've had Ian Poll on, and I was fascinated to hear his episode. Have you ever had anyone from Eurocontrol, and specifically, have you ever had Rachel Burbidge?
That's a good wish. Okay, you placed your wish. I will try to do the magic now.
She would be great.
Thanks, Paul, for that. And before we end the episode, a big thanks to Kieran for preparing and asking very smart questions here. And I think it was a great appearance. So thanks a lot, Kieran.
Yeah, it was an absolute pleasure. Really enjoyed it. Thanks for having me again.
And of course, a big thanks for our guest, Professor Paul Williams. Paul, it was a pleasure, very insightful. And thanks for being here.
It's been an absolute pleasure, Marius and Kieran. Thank you both for organising this podcast. I think it's really a vital contribution to the debate around aviation and climate, and I wish you the best of luck for the future with it.
Great to have you, Paul. Thank you. Bye.
Bye-bye.
Speak soon.